Sounds good.
All right, Pranav, it's all yours.
Sounds good. Let me just share the presentation on screen. Cool. You guys can ignore the sirens going on, but we can go ahead and get started. So like Alan mentioned, today we're going to be talking about semi-autonomous modes. And so it's a slight detour from the regular autonomous mode versus just manual control mode. And the reason why we think that this question is so interesting is because we think that humans are really good at some stuff, and we think that the computer is really good at stuff. And we think that a blend of both of them can kind of create something. We're kind of asking if a blend can create something even better than either of them alone. And so that's kind of the question that we'll be looking at throughout the entire presentation. And we've worked really hard and excited to show you guys what we're doing. Can you guys can see the presentation, by the way, right? The title slide and stuff. Cool.
Yes.
Sounds good. So, shoot. So the team, I'm Pranav. I'm a junior studying EECS at Berkeley. We have our team also has Dang Lee. Unfortunately, he couldn't make it today, but we've spent countless hours working on this project and designing this idea and stuff, and we're just really excited to show you guys the results. So the goals of this project, like Alan mentioned, are pretty broad. We want to show the overall goal is that we want to show that semi-autonomous vehicles can outperform fully autonomous vehicles and human-controlled vehicles. And the purpose, like why we're so interested in semi-autonomous modes, is because we think that they're much easier, easily attainable than like a level 5 autonomous vehicle, which might take maybe years, decades for us to reach. Semi-autonomous modes are very much in our reach. And so if we can prove that these semi-autonomous modes can outperform autonomous vehicles, then we might shift some of the development over to semi-autonomous modes because it's so easily attainable right now. And if it's more efficient, then obviously we don't need to spend so much money, time, resources in getting a fully autonomous vehicle if the semi-autonomous one is better. So, and the second reason why is that autonomous systems kind of black box the users. And so we think that the user is kind of an integral part of the entire system, right? Because they're going to be they're the end users. And so we want to focus design around those end users instead of just basically like have them sit in there and just do nothing and the system does everything around. So we want them to be a really integral focus of our design process and how we want to carry out our systems. So that's kind of the big goal. And throughout the presentation, we'll kind of take our steps to get there and try to answer that question of whether semi-autonomous systems are really safer, faster, basically just outperform the autonomous vehicles. So let's go into some background. These are the levels of autonomy. I'm sure that everyone here is pretty familiar with the levels of autonomy, but at level 0, we have 0 automation. So that's basically you have your throttle, your steering, and your brake, and you control all of them. There's nothing, whatever you choose happens, and there's no other computer-aided thing at all. And then on the flip side, we have level 5, which is basically full automation. So that means that you do nothing and you sit in the car, and you enter a destination and it takes you all the way. And so we're really interested in this space in the middle between level 0 and level 5 is where we think there's a lot of interesting things happening. And so we can go through. So level 1 would be something like a cruise control, something like that. What's important about level 1 is that the driver and the computer can't like simultaneously control it. So either the human is driving the car or cruise control is driving the car, but you can't have both of them driving at the same time. And then level 2 would be kind of where we're at with like the Tesla Autopilot. Tesla Autopilot kind of pushing it right now, but you can go on the freeway and then Tesla Autopilot will kind of control your vehicle. And you can kind of just keep your hands on the vehicle and make sure that the car is able to control itself in other situations, but the car kind of just does the work. And then level 3 is where we're kind of headed with like Poppy. I don't know if you guys know Poppy, the taxis driving around in SF, but there's a bunch of driverless taxis driving around in SF. And it's pretty crazy that they're able to do that, but they have an entire map of SF. And so like there's no driver at all. And like, it's only in conditional times of like, okay, if you're not an SF, you would need a driver or something like that, where you would need like some human intervention. And so these levels are pretty cool, but I think what's really interesting is that all these levels are kind of geared towards the race for level 5. Every single company, every single kind of automation thing is kind of running to reach level 5 first. And all of these levels, like levels 1 through 4, are basically what this autonomous level 5 doesn't have, if that makes sense. So these are kind of just all like the goal of these levels is to reach level 5. And so we don't think that these levels do a very accurate job of capturing maybe like a pure blend of like a semi-autonomous system where the human and the computer are both harmoniously interacting with each other and creating something that we think might be a lot better than maybe just a level 0 or level 5 combined. So we're really interested in this middle ground right here and see what we can do there. Yeah. So a lot of pushback from autonomous vehicles comes from the fact that there has been kind of a plethora of accidents that could be prevented with a human driver. So for example, there's one crash where basically a pedestrian was walking in the middle of the road, and then the autonomous car wasn't able to see it, and it crashed into the pedestrian, resulting in a death. And so these are the kind of news that make us think that if I was driving or if you were driving, we would have seen the pedestrian like in the middle of the road, but the autonomous agent wasn't trained for it. So clearly there's some pushback in that we think that humans are better than computers at certain things, like understanding the context of your environment and like being able to read different things in a very fast amount of time. And so there's definitely some things that make humans better than a computer. But then on the flip side, we also have 1.35 million car accidents every year. And so 80% of those car accidents are caused by inattention to driving. So basically, if you're not paying attention to your environment, you're not paying attention to the road, that's 80% of the 1.35 million. So clearly that's something that a computer would be very good at, right? Like just paying attention to the road and the environment around you. It's something that we think that computers are better than humans at and can maybe minimize this 1.35, which is the reason why we're pushing autonomous vehicles so much. Is a big factor is the safety. So the kind of motivation for this project is that humans are good at certain aspects, such as like understanding the environment, whereas computers are not so great at it. And computers are really good at like doing what they're told to do. And humans can sometimes slack off. They get tired. Computers don't get tired, but they can follow a line very easily. So there's pros and cons to either of them. And so we want to take the pros of both humans and computers and make something that's hopefully better than either of them on its own. So now the question comes for why are we doing this with the Reward Lab if we want to do it with everyday vehicles? Like why are we focusing on like in a racing context? So one reason is that racing is just cooler, right? We like cars that go fast, but also racing is the pinnacle of innovation. So a lot of the things that we see in everyday cars actually come from motorsport. So in your Prius, the regenerative braking actually existed in a McLaren 30 years ago. And so they invented regenerative braking so that they could harness this extra energy so they wouldn't waste it. And today it's used in cars all around. Buses use regenerative braking. It's a very critical technology in the automotive industry. And so it's pretty crazy to think that this came from motorsport. And so that's the big one. But there's so many of the things that we use in everyday cars are coming from motorsport. And the reason is because we need to, like in motorsport, you need to shave off seconds of a time. Performance is so critical in motorsport. And so this is where we have these kind of innovative ideas of how do we extract the most performance out of any given technology and how do we make it better. And that's why we're doing the project with Roar specifically, is because we think that if semi-autonomous mode can prove itself on the racetrack, then it can prove itself on regular roads as well. So that's kind of the context of why we're doing it with semi-autonomous modes in racing. So you can go down the list, but I just listed 4 of them, but there's so many things that come from motorsport, especially from the safety side, because safety is such a big deal in motorsport. But like every car has a roll cage that's which is hidden in your car. But so that's why it's really exciting for what we're doing. So our project, I guess the goal is pretty simple. We just need to build some semi-autonomous racing agents and then beat the autonomous agents and the manual one. So we're kind of just setting up a race, and then we need to be able to, right now, there's no platform on simulation to kind of race multiple agents against each other. So we want to build up that infrastructure and eventually have some races between our agents. And we have a couple different semi-autonomous agents that we're working on. We have one that's kind of fully built out, and so that's the one we'll be covering today. And so the motivation behind that is basically we're going to take a look at F1. I watch a lot of F1 personally, and this is kind of what sparked the idea for this project, is that basically there's something called a racing line for the racetrack. And so the racing line is basically the path that you can take that will result in the fastest time across the track. So this accounts for vehicle dynamics, aerodynamics, basically a bunch of stuff that has to do with the vehicle. And also, usually the vehicle goes like faster on straight tracks than on turns. So the point is usually these race lines kind of elongate the radius of each turn, as you can see on the right, to try to get the most straightaway that you can on each of the turns. And that usually results in the fastest time. And so the more that I dove into F1 and motorsport, I realized that the fastest drivers, the people who win these F1 races, actually don't follow this racing line. So they follow it like pretty similarly, but then there's some moments where the driver realizes that the racing line is not optimal for me to take. Even if it results in a faster time, like with the other cars and like in an actual race, there's going to be other cars there. So you can't simply just follow the racing line. And there's so many other things in play. And that's something that the driver makes the decision of. And so that's something we thought, okay, so the human driver is more capable than the racing line calculator, right? The computer. And so this is the reason why we kind of think that there is some blend of computer aid and human aid that can win races completely, because racers have a hard time following this optimal line, but a computer could do that really easily. We build line follower robots every day, and so we can try to build that easily with some PID agent or something like that. But the human racer knows when to speed up, when to slow down, how to block other cars, how to use the cars in front of it to get some aerodynamic advantage by drafting and stuff like that. So there's a lot of things that the human racer knows more than a computer, but also where the computer can help out with the racing line. So that's kind of the motivation for our car. You guys can see my friend Lightning McQueen from Cars 3. If you guys watch that, he's on a simulator where the blue arrow is the racing line. So he's trying to follow the racing line as best as we can. And so the agent that we built is able to follow the line. So our first test is to take a PID agent. So we're just going to draw a line on the track, which we think is the most optimal racing line on the track. And then the PID agent will just follow it around in a circle. And so the semi-autonomous part comes in when, like me as a human, I can control that PID agent and kind of shift it off of its track. So for example, if the PID agent is going in a straight line, I can increase the throttle for the PID agent so that it can go faster. I can like slow it down by reversing or braking, or I can kind of shift it slightly off of its track by turning left or right. So these shifts are very minimal in compared to what the agent is outputting. So the agent will still follow the path, but the human can make slight adjustments to that track by like judging their own input. So for example, if a computer can only see like maybe 10, 15 feet ahead of it, but as a human, I can see 25, 30 feet ahead of it, I can go faster because I can see farther in front of me. So I could increase the throttle at that time to make it go faster. Or if I see like in the future, there's a pedestrian walking, but the computer doesn't see, I can slow it down from my end. So basically we're just adding or subtracting throttle and steering to the original path, but we're not actually changing the path itself because the PID agent is going to follow it. So that's kind of that's the first agent that we built. It's a very simple agent, basically just taking in both, simultaneously taking in both human input and the PID agent. So technically, if there's no human input, the PID agent will just follow its line on its own. It'll just technically be zeros if you're looking at like addition and subtraction. But yeah, let's take a look at what it looks like on the track for results. So on the left, we have the original PID agent that just basically follows the waypoint. And then on the right, this is me trying to drive it. And then I can basically add some turning, some throttle, brakes. I can control all of that. So I'll start the PID agent first, give it a little head start, and then we'll start ours. So this is on the same track, side-by-side comparison of how it's going. So if you notice, the car on the right is going a little bit faster because I can see farther ahead of it than the PID agent can. So, and then I don't know if you guys can see the throttle on the left. If you guys can't see it, I can zoom in after the presentation and have questions. But basically, like on the left, the throttle is changing all the time because the PID agent doesn't know what's going to happen next. But since I can see what happens when it's a straightaway, I can just click the throttle full all the way. And you can see like whenever the car is getting out of control, the brake lights turn on, and that's because I'm physically braking the car so that it'll slow down and be able to regain control. So as you can see, the PID agent plus human control is able to go a lot faster on this track because I'm able to speed up and slow down whenever the car is driving. I also did not include one video of me driving alone because on the turns, I would just crash on every single turn, so I wasn't able to make it. But here, the PID agent is helping me kind of navigate those turns. And if you can see, like on the turns, the throttle goes down to 0 because I just let the PID agent do whatever it wants because I'm not that skilled to basically do those turns. But so right now, the one on the right finished and the one on the left is still running. We can wait for it to complete. But I think what's really cool is that like the PID agent plus human control was able to create something that was better than me controlling it on my own and the PID agent on its own. So, starting. So the relevance is, it's pretty crazy that this is a very simple test, right? We don't want to use, obviously we have much better agents than the PID agent. We don't want to use this as like a benchmark, but like in principle, we have proved that there is some middle ground in between autonomous and a manual control that could be better than both of them on their own. And so we want to use this principle to kind of create more agents that'll hopefully be able to beat any of the autonomous agents as well. Because in this simulation, we could have replaced a PID agent with any agent. So I could have built a OpenCV kind of agent and then race it against this one. And then the human could still help it in some way. Or worst case, if the human doesn't see any way to help it, if the human does nothing, then it'll still output the same kind of controls as the regular agent. So with a skilled human on the track who is not trying to sabotage your car, this kind of agent will never perform worse than the agent on its own. So it's a pretty neat kind of representation. And I think it's also cool because this agent will be able, like we can use it as a testing tool for different RL environments. So we can kind of add noise to it and see what happens and kind of go from there and see how the autonomous agent reacts to not being able to fully control its environment. So those are real results, but the big kind of conclusion that we got is that there is something in between autonomous vehicles and fully manual control that's not included in the level. So I don't think that this is something that would be included in the levels of automation, right? But there's some kind of blend, like some harmonious blend of human and machine interaction that will help elevate drivers to kind of a new level and be able to control their car, be safer. First of all, most importantly, be safer, but also go faster and have better performance. So it's pretty interesting to see how the semi-autonomous field will adapt and change over the next maybe a couple of years and see if that's something that people will be more invested in. There's already so many different semi-autonomous modes that exist right now, such as like lane assist, brake assist. Cruise control was obviously the first one, but it's interesting to see whether more of these will adapt or whether we'll still continue trying to go to the full level 5 and see how those paths kind of diverge. But yeah, so for the future work, so right now we tested it with the PID agent. We want to test it with the reinforcement learning agent. There are slight complications with testing with an RL agent because the RL agent uses a reward function. If you guys haven't watched the seminar on reinforcement learning, it's pretty good, so I watched that. But the RL agent uses a reward function. And so basically when the RL agent realizes that it can't control the world, the environment that it's in, it might break. So we're thinking about new ideas for how we can kind of systematically shift control to the human and back to the RL agent in a way that would make it really efficient and make the agent better and not worse. So that's something that we're looking into right now. And then another thing is that we want to be able to, right now I showed you a side-by-side of 2 different lap times, but we want to be able to actually see the cars interact with each other and see how the cars are able to kind of beat each other, overtake each other. Maybe they're able to draft against each other, go right behind each other. But we want to see that in real time. So we need to build the infrastructure for how to see that. And finally, we want to keep building these semi-autonomous agents. These are really cool. I think that it was pretty interesting. I don't think I've seen any other research papers like this dealing with trying to blend them together. And I think that it's just a really interesting space right now. So yeah, Dang and I are really excited to continue building like maybe something that can overtake, because overtaking is pretty dangerous sometimes. So we want to see maybe a computer can help a human overtake and make it safer or something like that. But we want to keep building these and testing them against the original human controlled and autonomous agents and see. But yeah, that's all for me. Thank you so much for listening, Professor Alan Yang and Professor Shastri, for the resources. But if you guys have any questions, I'd love to answer them.
Yeah, thank you, Pranav, and I will try to ask the attendees to think about questions and then to ask. I will start with a few questions myself. Yeah. Number one is that in your comparison of PID versus PID plus manual control, did you ever change the steering, or you are primarily contributing to modifying the throttle and braking?
Yeah, so for this one, for the PID agent, I mostly contributed to modifying the throttle and braking. I think that the steering would come more into play when there's other cars present. So right now there's only a single car on the track. So there's no real need to change the steering because we're not trying to block a car. We're not trying to overtake a car. So we can just follow the path on its own and change the throttle and steering. But I think it'll be really interesting to see how, when we have 2 cars together, how we can change the steering to kind of maybe block the other car off so that it doesn't overtake you, or to see how we can overtake another car by changing the steering and making it more like the F1 example that I showed in the very beginning of right here, of how we can kind of change the steering to veer off the original path. So the green path, so here the green path is the actual race line, and then the red path is the path that the driver takes. So it's interesting to see why the driver chose to take this path instead, and maybe the other cars will influence that. And so we can actually make this happen in our agent. So it'll be exciting to see that.
Right. Right. So just to clarify that in your PID, the throttle and steering are 2 different PIDs, right? So you are changing the value, or the computer realizing that the throttle and braking are not exactly equal to the output of one PID, does not stress the other one.
Yeah.
But you said that in reinforcement learning, if the same agent is doing end-to-end, then the execution of the control does not exactly equal to the output, will lead to some stress to the model, because then the model prediction and then the real outcome of the environment update become different, right?
Correct. Yeah. So the PID agent is just using simple waypoints. So changing the throttle and steering, it'll just try to guide it to the next waypoint. But for the RL agent, it'll kind of mess up the entire reward function, because it might just break because we don't know, it doesn't know how to handle this new environment variable that it can't control.
And then I have a second question about the manual control. In terms of the color, to what detail you can manually control more lower level subsystems? For example, can you, I'm just saying something out loud, right? So, for example, I think that you mentioned a really cool idea of using semi-autonomous driving not only for the purpose of increasing the winning team, right, but you can also simulate some adversarial conditions using manual control, because the autonomous control will never create adversarial conditions. So in Kala, to your knowledge, do you know that you can manually, for example, lock one wheel, or to what detail you can create using manual input to create adversarial conditions that a optimal auto agent will never interject themselves to create negative conditions.
Yeah. So to my knowledge, you don't have that much control over like making like a specific wheel lock, or maybe like having the car turn suddenly randomly. I think that those are all like predefined, like the ego kind of like the agent does it on its own. So I think that that's why this might help out with that. And so like from at least what I know, I don't think you have that much control over it. I've definitely I've spent some more time with Ross and Carla now than I have before over the last couple of weeks. So maybe I'll find something the next couple of weeks. But at least from now,
but you can create jittering,
yeah.
right?
Yeah.
Because in Kala, we know that we cannot simulate environment elements. For example, raining, snowing. Even if in Unreal Engine, if you ask the Unreal Engine to snow to rain, the road condition is still the same.
Yeah.
So you could insert unpredictable steering noise
to
the
vehicle.
Is
similar to, I think, the push cart that we were talking about, the video, like a push cart, kind of the video shaking a lot or something. We could simulate the jittering of the car similarly to that, and see how the cameras and LiDAR react to that.
Yeah, so it would be nice to have a report of how much of these variations deviating from the optimal condition the current software stack can simulate, can manually inject. So I think that will be very, very useful for testing purposes.
I think if we had like a camera side by side or something, and a report of how the camera would change or how it would react to that, that would be pretty cool.
Yeah. So there's great. There is a question. There's a question from Aaron. So he asked, what kind of a semi-autonomous agent do you plan to create next?
Yeah, so we actually had two different ideas. So one was drafting. I'm not sure if everyone is familiar with drafting, but drafting is the concept where kind of there's like one leading race car, and then the other race car just follows it right behind it. Like it just follows it. If this one turns right, it'll turn right. Like it'll follow it precisely. And so the reason race cars do that is because there's like some aerodynamic drag that's coming off the back of the previous race car. And if you get right behind it, you can kind of escape you can get kind of like a boost, because you're in it basically simulates you in a wind tunnel when you're behind a race car, because the race car is punching a hole through the air and you're kind of going straight through that hole. So you don't have any extra air resistance. So I wanted to see kind of if we could make instead of like a line follower, we could make kind of like a car follower that would be able to closely draft, because drafting is pretty hard for, I think, regular humans to kind of do, because you need to be following a car very closely, and it's pretty dangerous. So I think that's something where a computer could really help out, because it can maintain a certain distance pretty easily, and it can see where the next car is moving and try to follow it. I think another really interesting agent that we've been thinking about is an overtaking agent. So maybe when it sees a car, you could give control to the computer, and the computer would overtake the car in front of you, and then you would regain control after. So since overtaking is I think it's almost an art when you see it in these motorsport races, is overtaking is very difficult, and a lot of humans can't do that. And so maybe that's something that the computer could make safer, and maybe better, overall is better, because it can calculate specific lines and stuff like that for how to optimally overtake a car. But yeah, so those are two different agent ideas that I was thinking about. But yeah.
Okay. Are there any questions from the audience? There is a text message again from Franco. The question was that it seems that you and the PID agent are to end-to-end progress, and you will take full control whenever you believe the PID. Well, I think that your presentation did not actually represent what Franco was saying. I don't think that you are taking full control. So, but I will let you answer that.
Yeah, I can clarify that a little bit more. So I can go back to the video. So basically, I never take full control, actually. So instead, what I'm doing is that I'm basically superimposing human control onto the agent's control. So basically, like the agent control will just be on the bottom, and like that will output, let's say, like in the Carla environment, the agent outputs throttle, steering, and brake. So there's 3 different values that the agent outputs. And so then let's say like I'm on my Xbox controller and I hit like the throttle up a little bit. Maybe the throttle, like the human agent throttle is like 0.2. So if the agent's throttle is 1, then it'll just add the 0.2 onto the 1 throttle. So it'll be a total throttle of 1.2. And then if the human is not moving it at all, it'll count as a value of 0 and add 0 to 1. So technically, we're never switching control. So both the agent and the human has control at all times. So we're never shifting control between the human and agent. We're basically just superimposing anything that the human does onto the agent. So if let's say like the steering, like the agent has a steering value of 0.5, and then the human gives it a steering value of negative 0.5, then it'll not turn at all. It'll go straight. So the point of superimposing human control onto the agent control is to hopefully make something that like the agent will follow this racing line perfectly, but then whenever you need to kind of move off the racing line or kind of make any adjustments, you can make slight changes that won't affect the entire path on its own. So I hope that clarifies a little bit. Otherwise, I'm happy.
Hey, Pranav, as a follow-up question, you are using an Xbox controller, right? So therefore, you can add on incremental changes rather than using keyboard.
Correct. Yeah. Correct.
And then you are mapping the steering and throttle and brake to different controls on the Xbox.
Yeah. So I mean, the throttle will just be like the front and back of the R2, R1 arrow. And the steering will just be the knob. For braking, so braking is the one thing that if the human brakes, then it'll override the agent control brake. So if like there's no.
But is the braking also analog in the sense that is there a braking that is from 0 to 1 or?
No, yeah. So braking is true or false. So basically, the braking just goes if either the agent brakes or the human brakes, then it'll just brake on its own.
So is this a limitation in Kala? Because the real car can assert a different level of braking.
Yeah. So the vehicle. So there's a vehicle control a data structure that Carla uses to control, and so in that one, the brake is a Boolean. But I think there's a different structure that I saw that uses as a value. So I might switch over to that one, having brake as a value, so you can like brake harder or brake less depending on how you're going.
Yeah, it would be nice to do that on an analog scale, and I think that you can use one of those triggers on the Xbox.
Yeah.
That will also output analog values rather than Boolean values.
Yeah.
Yeah. Okay. Are there any other questions?
I had a question, Praveen Kumar.
Yeah.
In the demo that you showed, so the main reason that the human driver was able to move faster was because you could see further than the sensing on the agent. Is that correct?
So in the PID agent, it's a little bit different. They basically have waypoints, and then they have like a PID speed controller as well. So the speed was kind of limited by like the waypoints. So like it tried to reach the next waypoint in a certain amount of time. But we're not, basically like the human control is not limited by those waypoints anymore, because we can just go as fast as we want. And still be safe while doing so. Whereas the PID controller doesn't know anything past the first waypoint. So it doesn't know if it can go really fast or not, because it's like its only goal is to reach the next waypoint. So that's all it sees. So yeah.
The waypoints were more spaced out. Would the PID agent move faster?
Yeah, so like I think it's like a question of like if you have a line, like a line can be represented by like 2 points, right? But let's say like the PID agent is putting like 5 points in between those lines. So like even on like a turn, you can represent a turn by like how many points. So it's like if the PID agent had less waypoints, then I think it could go faster, but then it would still be limited by like on the turns, it wouldn't know exactly where to go on the turns. It's like so like it can only see one step ahead of it. So regardless of I guess how little or how many waypoints you had, there's still a limit of it doesn't know what's past the next waypoint.
So I can give additional information to the question, and thank you for the question. There are two additional considerations to this question. Number one is that as far as I know, the current implementation of PID, the basic PID will have just one value for the whole track. So therefore, you could, based on whether you are on a straight line or you are on a turn section, you can change the PID. So that is, a region-based PID. So that is equivalent to your racing driver switching your knob to, condition 1, condition 2, condition 3. Actually, if you watch Formula 1 racing, the radio control sometimes actually asks the driver to switch to mode to different conditions. The reason is because the road is wet or the gas is light. They actually tune different parameters of the chassis for different conditions. I don't believe that Pranav's version of PID is region-based that is optimized for every section. So that is one thing. The second thing is that the PID, as far as Berkeley's version, is a look-ahead PID. And that means that when you are driving the vehicle to the next waypoint, you really cannot use immediate next waypoint, because if you use immediate next waypoint, the car is going to jitter. It's going to zigzagging. When we do the waypoint-based PID, you want the waypoint to be looking ahead a little bit. So the immediate next destination will be the average of a few future waypoints. I think what Pranav was saying is that for humans, depending on that you are on a straight line or you are in a curve, so the human can look ahead and dynamically switch waypoints. But for the current implementation of PID, I think the look ahead waypoint is fixed. For example, it's the average of the next 5 waypoints or the next 10 waypoints. But I do not believe the implementation dynamically extending the future waypoint look ahead to be dynamic. You could do that. So the question remains that if you implemented all of the above, which will be not the standard PID, whether it can match the human input, like Pranav manually inputted as a human driver.
Thank you so much for the answers. Yeah, that's super helpful.
Yeah.
I suppose another benefit of this work could be that in any of these experiments, if you're finding scenarios where the human driver is consistently beating the agent, those are all probably ideas around, it could probably give you ideas on how we could improve the PID agent, I guess. It's sort of like learning from the human and seeing, what you could do to keep improving the agent to get better and better.
Yeah. You can also use it for like some imitation type of learning.
Yeah, right. Yeah, kind of. Yeah, sort of.
Yeah.
Good work. Yeah. Thanks for the answers.
Thank you.
Okay. Yeah. So it remains to be seen, right? So if we know that that's why Pranav is modifying the input, whether then we can use that to change the PID to have a smart PID. That remains to be seen. The current PID is hard coded. It's not smart. Itself is not smart, but the parameters are tuned by the human based on the experience. Yeah.
Okay, great.
Okay, are there any other questions from the audience? Are there any questions? So if there's no questions, I just want to conclude by saying that in the next semester, what we are planning to do, one of the interesting questions is to considering added human control as a concept of co-pilot, but making the reinforcement learning to be compatible with the co-pilot, which means that knowing that it's not alone. So there's a human that will work with the reinforcement learning. So I don't know how deep the current research has been in this area, but I would think that it will be an interesting topic that will based on what the Pranav has already gotten. And then the second one will be intentionally trying to make the driving condition worse, making the human input as adversarial, and then see if the intelligent system can overcome that. So that to simulate the real world condition that may be inserting uncontrolled changes to the vehicle dynamics. So I think that these are the two main areas where we can go from the Pranav's results this semester. Okay. Yeah, and yeah, so I will. If there's no other questions, yes, I will. I would like to thank Pranav and his team to contribute to this semester's research in a relatively new topic. And I think that the other teams would love to look deeper into the semi-autonomous direction and see, for example, in the two areas, what we can do for the next semester. Okay, thank you, Pranav, and thank you everyone for coming.
Thank you.
Okay, bye-bye.
Yeah, thank you.